Today we will take up a new topic. This is on induction generators. In this course we have been taking up those areas or topics which are considered special, considered non-conventional and considered not very old or which are likely to have a impact in future. So, that is why I have chosen this topic under this category of special electromechanical systems, okay. And I have a reason to do so, okay. Now, if I ask you a question, which do you think is the biggest threat to mankind, for the survival of the mankind? If I will ask you one single answer, which is the biggest threat to the survival of the mankind? What do you think is? Can you give me one single answer? Power failure. Okay, you say power failure is one threat, biggest threat to mankind is power failure. But there were people who were there when there was no power also. Okay, this is one. Then oxygen is there still, it is yeah. As of now, that is not oxygen is not likely to vanish, hopefully. So, any other more immediate, more important threat to the very survival of the mankind? Global warming. Then okay, global warming is more nearer to the threat, okay. Or in other words, you can say the biggest threat is the climate change, right, which is already been predicted by scientists that the climate change is one which is likely to create havoc to the survival of the mankind, okay. Global warming is one part of the climate change, glaciers melting, okay. Then you have the CO2 emissions, greenhouse gases and their impact, ozone layer depletions, okay. So, these I hope at least you as engineering students have to be sensitized to this, okay. Because these are, so every technology, what is the technology is for? Technology is for survival of the mankind, technology should not be for destruction of the mankind, okay. That is not meant to be. So, technology is to improve the quality of life of the mankind, not to provide a threat to the survival, okay. So, there is we should not say that we do not bother about the deluge which is likely to come maybe centuries later, okay. Therefore, we need to have the future generation into account, okay. Now, what are the factors which is likely to cause this climate change? Next question, what are the factors? Huh? Okay, pollution you say is the one which is likely to create problem. Why the pollution takes place? What is the reason for pollution? I am just answering, you say there should be pollution, which is creating problem for the mankind, okay. But the man has been polluting this earth for a long time, only new type of pollutions are coming, okay. Now, what is so great about it? Why is it you think it is a very big threat? How is it, what type of pollution which you think will create problem for the mankind or which will lead to this climate change? Okay, air pollution. You say air pollution will create so much problem for the climate change. Why is it so? What is it? Why is that air pollution is creating such a problem? Huh? Industries are there. Industries have been there. Okay. Okay, industries are creating problem, then you want to stop the industries, close down the industries. Hmm? Okay. So, you are nearing the answers, but you are not really being able to be focused on what are the factors which are likely to create climate change, which in turn will create a threat to the mankind. Okay, right. So, it is this, as I have already mentioned, it is the greenhouse gases, CO2 emissions, okay, then ozone layer depletions, right. All these things are affected because of what? One central theme, is for all these things, the reason has been the problem of providing energy to the people. Energy is becoming, there is not so much problem providing food to the people, but there is always a problem of providing energy to the people. Okay. And it is recognized that energy is central to the quality of life. There is certain per capita consumption of electricity per year is considered necessary for you to maintain. Okay. And fortunately or unfortunately, the per capita consumption of electric energy has been increasing over the years or decades. Of course, there is a vast variation in the per capita consumption across countries. Developed countries have several order of magnitude compared to developing countries like India or China. And you are also should be aware that the two countries which will continue to have the highest rate of growth of power generation will continue to be India and China. Okay. India is having 130,000 megawatts of installed capacity and it has to double it in the next 5 years just to meet the requirements of the people. Okay. And so, how do you balance this? You need electricity, you need energy requirement for the people, but then it will create problem for the global environment or climate. Okay. And the developed countries are not prepared to perhaps sacrifice their requirement of energy per head. Okay. And now we need to work out a system in which we should generate energy or electricity with minimum impact on environment. Okay. So, that is the ideal solution. Climate change takes place because of the thermal power plants, and it leads to air pollutions. In some place, if there is heavy sulfur content in coal, it leads to acid rains. Okay. Right. And therefore, that is one problem. Nuclear energy, some people say it is less polluting, but it has its own impacts in terms of radiations, etc. Okay. And the petroleum products, whether it is through transportation sector or power generation sector, either the crude oil use in different formats, whether it is through gas, whether it is through diesel or whatever. So, they all have their own problem of pollution of the surrounding environment. Okay. It is not pollutionless. Okay. So, you have to think of pollution free electricity generation. Okay. That is the objective of this. So, there has been emphasis in last 20-30 years to go for the so called renewable energy systems, isn't it? Renewable energy, which can be renewed, it does not pollute. Okay. Hydro was one of the largest renewable energy, fortunately. Okay. Though some environmentalists say that large dams are also create ecological problems. Okay. Maybe deforestation, greenery is removed, etc. Okay. But at least you can think of small hydro or a mini hydro or a micro hydro. So, they are all the one which will be likely to have an impact. See, for example, India has nearly 50,000 megawatts or more of these hydro potential, small hydro potential. Okay. And many of them are not tapped in Himalayas. A state of Arunachal itself is having half the hydro potential of the whole country. Okay. So, obviously, one has to think non-conventional, think of these mini hydro or small hydro systems. Okay. And another area where you can produce electricity is the wind energy. Okay. And fortunately, we have enough of wind intensive zones in India. Okay. And again estimated potential of wind energy in India is around 50,000 megawatt, okay, which is almost 50% of the current installed capacity, right. Therefore, it is again a promising area of power generation. But since these are non-conventional, technology will be non-conventional, you have to work out proper designs of the technologies for this. Okay. And both in this small hydro and wind systems, the generators which are used or which are recommended to be used are the induction generators. That is why I took this topic. Okay. So, till earlier people did not bother about induction generator. What is induction generator? It is basically induction motor operating in the generating mode. Okay. Because induction motor is rarely used as generators. Okay. And while there are large number of manufacturers in the whole world making induction motors, there are very few who make them and sell them as induction generators. Okay. So, induction motors are major workhorses consuming nearly 60 to 70% of electricity produced in the world. Okay. Whereas on the other hand, synchronous generators are the ones which produce power to the world. 90% of power is produced through synchronous generators, again alternators. So, again synchronous machines are generally sold as synchronous generators or alternators, right. You see the other side of the story. So, synchronous machine is bulk for generation, induction machine is bulk for motoring, is it. Now, we are looking at what are the issues involved in using induction machines as generators. Okay. Incidentally, in maybe in 1985-86, I proposed this to one of the companies in India to make induction generators for wind applications, because wind applications one where most of the generators are induction generators, wind machines. And they were engineers or designers in that company were uncomfortable, because they are quite happy with designing motors. Then they told me that you are unnecessarily creating as a problem by giving a new product to our management, that they will make us to work more and understand new things. And there was, I had to give a special lecture to these engineers there, because there are a lot of misconception of induction generators. Some people say it takes leading var, all type of things are there. Okay. Now we have to, why I chose this topic for you is that you should not have the confusion which many engineers in industries are having today. Okay. So, we will discuss about the induction generator starting from the principles which you already know as induction motors. Okay. From there we will show, and a induction motor work as generator in what mode? When will it work as generator? When it is working beyond the synchronous speed, okay, that becomes a generating mode when the frequency is less than the speed, right, in per unit basis. Okay. So, we will these induction generators, right, are used or IGs, okay, and they are used on two modes. Okay. One is connected to the grid, right, you feed it to the grid or you make it stand alone. There are two modes, is it clear? Induction machines, even synchronous machines can be standalone. A generator at your house is standalone, it is not feeding to the grid, where a generator in the power station is connected to the grid. So, you can have a induction generator which is fed to the grid, or you can have induction generator which is just giving the load, local load, okay, right. So, this is the one which is fed to the grid, okay, this category 1, and this is the one which is standalone, let us say 2, okay. And grid connected, when this is fed to the grid, what are the type of machines you have? So, it is called a grid connected induction generators, or I call it as GCIG, okay. Let us see what types further are there. One is a squirrel cage induction generators, that is SCIG, squirrel cage induction generators, where a normal squirrel cage machine, I hope you know squirrel cage machines, isn't it? I hope nobody has a doubt on what is a squirrel cage machine, okay. And then squirrel cage machines are also, there are two types are made, a single winding or a dual winding. In the stator there are in wind machines, you know, it is the wind machines are the one which operate at varying speeds or varying power, right, because power which is going to the wind changes with the wind speed. After all, sometime wind may not blow, okay. So, you must catch power when there is wind, okay. So, you must really capture the wind power, right, and which is you can't control the wind power, right, you can't put fans around and say we will produce wind, okay. Therefore, you need to be very clear, then this varying power is achieved through, you can have one high, same machine can operate sometime at higher speeds, some at lower speeds or whatever. So, what it will each will have a one could be single winding you can't have a much control, dual winding you can have a control, two windings are there, okay. Then the other portion, other one is the wound rotor, this is one of the latest one, and some companies have now taken some patents on this. This is the latest, that is the wound rotor machine. In fact, we were not propagating it earlier because it has brushes. As I told you, brush is a nuisance for electrical engineers because where maintenance, parking and all the problems are there, okay. So, this has brush, when it is wound rotor you obviously need a brush, okay, brush gear is required. And this is doubly fed, if it is a wound rotor you can feed it from the stator, you can feed it from the rotor, whereas squirrel cage you can't feed it from the rotor, rotor is closed, in a squirrel cage rotor is closed, right. So, this is one factor, okay. Then this whole thing is about one which is feeding to the grid, okay, and there is another one which is standalone, okay, of this type. See, you know, induction generator has no excitation to give, okay, unlike in a synchronous generator where you can pass a field current through another DC source to the field winding, it will produce the flux. But I give you an induction machine, you go on rotating as much as you want, right, from the prime mover, will it has any voltage induced? I'll give you an induction motor, give you an engine or a prime mover, okay, you go on rotating the rotor, okay, will it produce any voltage? Huh? So, it does not produce a voltage. Now, we have been working in this area for quite some time, we have what is known as self excited induction generator, SCIG, self excited induction. You make it self excited. What you do is you connect, you fix a capacitor here, a charged capacitor, then what will happen is, you know, any generator which is a capacitive load will be magnetizing effect is there. So, it is sort of a resonance you can say, machine is electromagnetic and capacitor is electrostatic. So, there is a exchange of energy between the two, it will become self excited. We will discuss it later in detail. So, these are the two things which we have, this self excited. So, you can think of both modes, okay, and this is I mean your construction, I hope you know about the large induction machines. This is the stator, a wound stator of a induction machine, is a 3 phase winding which is there, of course rotor will get in, okay, and of course, this person is an IIT Delhi student in a company, okay, stand where we took the photograph. Okay. Now, this is of course, it is small, I hope you can see. What type of rotor is this? This is squirrel cage rotor, okay. I hope you know. So, this is a squirrel cage rotor shaft, it is a big one which you get into this, right, okay, and there are the bars, end rings, the fans and fins and other things for cooling it, okay. I think construction, you should not have any doubt at this stage what is the construction of. Stator has 3-phase winding, rotor has squirrel cage wound multiple pole winding, okay. Now, this is one picture of a wind farm, okay, in a place Chitradurga in Karnataka, okay. So, what you see here is you can see there quite a nice site. It was earlier a barren hills, okay, and you see, and they have put, I mean, these are all the roads which were made, but these are all the GE has supplied these machines, okay. You can see how they are located, and they are all run in the same direction, you observe. It is not that one is in east, another is in west, it is not there. Why? It will always be tracking the wind direction. So, all all machines is 100 machines, all 100 machines will be in one direction, okay. And it is quite maybe the height is quite high, maybe as high as Qutub Minar or whatever, okay. As I mentioned to you once, the today's blade sizes are as big as a football field, okay, and the ratings go to 4 or 5 megawatt each, okay, and they are made, lot of them are offshore, okay, and you will see all the the power is converted and it is fed to the substations here, right. They are collected and then fed to the then taken out to the grid, right. So, there is generation in each of these machines, they are connected, they are all feed to the grid, right. Now, how does a wind machine, I think this is the blade, okay, and there is a gearbox here. This thing is the gearbox, right, and this is the coupling here, and this is the induction generator, okay. It is driven, I mean, through a gearbox, because the wind speeds are low, you step up the speed through the gearbox, and there are two induction generators, you will see the big one and a small one, right. And the big one will operate when the power is more, and the small one will operate when the power is less. This is a typical system. Of course, the whatever power the generator will come to the below for the control panel here and goes to the grid. And there is what you see here, you see something here, okay, it is an anemometer which measures the wind speed and wind direction, okay, and which will go to shift this. This whole thing is called an SLA, whatever on the top, it is called SLA. It is like and which goes on moving towards the wind direction, okay. I hope you have some idea of what is the wind systems look like, okay. And there are a large number installed in Tamil Nadu, this is number 1 state, and they are in Gujarat number 2, and others are in to some extent Orissa, southern West Bengal, Madhya Pradesh, Maharashtra, Andhra Pradesh, Karnataka. These are the ones, these are the regions where there is a good wind regime. And you will also notice in India, fortunately, where there is large wind, there is not much hydro, right. So, it is complementing. Most of the hydro is in the Himalayas range, then where there is not much wind, okay. So, that way you have a good geographical distribution energy sources, renewables, and wind is expected to be one of the important parameters, important sources of energy, especially for India. And today India is the 4th in the world in terms of installed wind power capacity, nearly about 5,000 megawatts we have installed capacity as of now, out of 50,000 which is the potential, right. And a lot need to be done as far as induction generators. Of course, some companies have been approaching us for development of these machines, okay. Since I happened to design the first induction generator for this country, okay, way back in 85 or so. Now the question is, with these potentials lot of technologies are there, and I wanted to emphasize this is one area where almost every engineer will have a role to play. There is aeronautical, before this there are meteorological scientist who has to tell you about the climate, then aeronautical, then there will be mechanical, okay. There is the civil tower person, and there is instrumentation, okay, and there is a computer and microprocessors, okay, control system, right, and power system, right. So, all it is a highly multidisciplinary area, okay, where it has to be seen, okay. And I told you India is 4th in the world. What are the other 3? Have any idea? Huh? Tell me. Well, you told what is not there, China. China is not the one, okay, right. It is others are Germany, Spain and USA, okay. Earlier Denmark was ahead of us, but we have taken India is ahead of Denmark in the installed capacities, but Denmark are still producing large wind machines, okay. I mean they are good at, historically the Denmark has been the wind Don Quixote's story you are aware of, okay, right. So, this is where we have to understand how this induction generator work and what are the problems, right. Okay, this we have seen. Now, it started in around 80s, okay. Unit sizes at that time was what 11 kilowatt in 80s, okay. Then it increased to 33 kilowatt, and in 85 I designed the 55 kilowatt, that was the first design, and that was the highest in 85, highest capacity was 55 kilowatt, okay. It was considered to be very big, etc. Then it went up to 120 kilowatt in Gujarat, it was installed in Lamba wind farms, went to 220 kilowatt, then went to 300 kilowatt, then 400 and 750 was there last 4-5 years, large numbers for 750 kilowatt units. Then last 2-3 years it has gone to 1 megawatt. So, this is presently the size 1 to 1.5 megawatt, okay. That is by this period, right. This is the range, and they are planning to equal to 4 to 5 megawatts single unit sizes. Mainly offshore is what is presently under development, okay, and installed, okay. Therefore, this is a schematic of the wind system. So, there is a wind which blows on the turbine, then there is a gearbox which drives the induction generator, okay. Is it clear? Drive induction generator, and which has a capacitor, mainly because induction generator you need a reactive power from the grid to magnetize the machine, because every machine you need something to magnetize. So, which we call it as reactive power. See, because you need to magnetize either DC machine, synchronous machine, induction machine, you need something to magnetize to put you can't have a permanent magnet. So, you have a magnetizing. So, induction generators are magnetized because it has to drive magnetizing current, right, from the mains. How does the magnetizing, so that it has to supply a reactive power from the mains. The mains has to supply reactive power to the machine from the grid, right. You have the grid here, okay. Now, if you connect some capacitors, at least the reactive power that is required will be reduced, having a capacitor here. then these are generally low voltage generation, then you step it up to 11 kV. So, nowadays you can go to the 33 kV or so. So, this is the grid where you are feeding it. Okay. So, whatever power that is given by the wind is fed to the grid, is it okay? Power from the wind is fed to the grid, but it takes the reactive power from the grid. So, this is a very peculiarity you must note. If it is a motor, you take power from the grid and reactive power from the grid and convert into mechanical power. Now, it is other way around, okay, because it is running at negative slip. Okay. Now, similarly you can use for hydro turbines. It is a wind turbine, you can use hydro turbine also, right, small hydro, mini hydro, etc. And this can be up to maybe up to 1 megawatt or something range. Okay. Sorry, so mini hydro is around 1 megawatt range. Okay. Okay, this hydro turbine has the same. What is the power in a turbine? You know, a turbine you may know it has a height, what you call it as head, and it has a discharge Q, and power is proportional to Q into H, right. That is the reason why I want you to know mechanical engineering. Okay. Turbine, it has to produce power, and this power is converted, and power is fed to the grid and reactive power is drawn from the grid, and other systems are similar. Okay. So, you can have induction generator both for wind as well as small hydro systems, and you do not need much control of the turbine here, whatever power is there you can feed it to the grid. Okay. The problem always is if it becomes a weak grid, this is the problem. It is 11 kV, it is 10.9 kV or frequency 50 instead of 48. So, then you have all the problems, right. So, that is what you have to be concerned about. Weak grid is an issue here. Okay. Now, the power in the wind is given by this formula. It is air density rho and a constant or a conversion efficiency Cp, then the dA is the blade diameter and W is the wind speed. Okay. So, these are the power in the wind. Therefore, you will notice interestingly, typical favorable wind speed would be typically some 5 to 12 meters per second, is typical. Okay. 5 is very low. If you say if you double the wind speed, you will notice how much power gets increased, 8 times the power gets increased. So, if it is giving x kilowatt at 5, it will give 8x kilowatts at this. So, there is a considerable variation in this, and also you have a d square diameter of the blade at the same position. If the diameter is doubled, you have 4 times. So, that is one of the important factors. So, you have structural designs are the limiting factors, how big you can have a blade, because sometimes they also have a blade controls also, there is a pitch control or the yaw control, where this is. So, there has been, if you look at last 5 years, if you look at the wind research in wind area, the considerable work has been done on this front, and recently IIIA has produced a special issue on wind energy, just last about 6 months ago it has been brought out. Okay. So, you notice the importance of this. Okay. Therefore, in the hydro, power is rho g QH, okay, where rho is the water density in kg per meter cube, the power in a hydro, okay, g is the gravitation acceleration, okay, 9.8, right. Then q is a discharge in liters per second and head is the h is head in meters, okay. So, this is the power in a hydro system. So, you need to know, and this much power has to be handled by the generator, okay. and so long as Q and H are constants, you will see the difference between the two is one is a constant power system, another variable power system. Okay. Right. Now, we quickly go these are things which you already know, is not it? Induction motor as a motor you are aware of. Okay. So, you are aware of this equivalent circuit. Anybody having any doubt on this? So, we need not spend much time on this, you know the voltage, resistance, etc. And this is R over this is S, which is 1 minus nu, nu is the per unit speed, is not it, as a per unit as a base is the synchronous speed, this you are aware of, and you are aware that these parameters are there which you have been, you are aware of these parameters are per phase basis, and you have the rotor parameters, the slip and the per unit speed nu. Okay. Then these are the supply voltages, and there is the air gap voltage. Air gap voltage is supply voltage minus the stator impedance drop, that is the induced stator voltage or air gap voltage. Okay. Then you have the, how do you calculate? You have the stator impedance, you have the rotor impedance, you have the magnetizing impedance, okay, and then you go find the net impedance, I mean solution of the thing. Then after the net impedance, equivalent impedance, then you know the air gap voltage, you calculate the air gap voltage, you can calculate the current, because current will be V over equivalent Z equivalent, okay, and sorry, okay, then you calculate the input current, you calculate the no load currents. No load current is after Vg, you calculate. I think you can do a simple have you done this programming? I do not know, I have done this, I have given this assignment, I do not know. Equivalent circuit, calculate the performance of induction machine, right, and then you can calculate the rotor current. So, you calculate the stator current, you calculate the no load current, you calculate the rotor current, which is the difference between this, and then you calculate the power factor, input power factor, you know V and I, you know the power factor, okay, power factor angle, okay. Then you know the input power, right, then you know the stator copper loss, you know the core loss. So, subtract that and you calculate the air gap power. So, whatever power that it gets from the supply, some is taken from the stator copper loss, some from the core loss. Okay. Then what you do is you have the air gap power, which will be 3 times IR square RR by S, and the rotor copper loss will be S times this, slip times PG, whatever power goes into the air gap, slip times that is taken away by in the rotor, okay, and then remaining becomes the power that is available to the, that is the developed power will be PG minus PCR, okay. So, 1 minus SPG, and then whatever developed power you subtract mechanical loss of friction windage, and what you get is output power. I think you know the power flow in a machine. So, you can calculate the developed torque T, developed power by speed, okay, and then you have the expression for torque, okay. I think these are all known to you, okay. I am just quickly revising what is the equations as a motor where S is positive. Now, your next thing is, if you make S negative, what will be the, so there will be a reversal of direction of power flow, okay, right. So, efficiency is whatever developed power by input power or output power by input power. So, there will be, so you know the efficiency. So, whatever is available at the shaft divided by what is what you are feeding to a terminal, you call it as efficiency of the motor. So, till that time there is no problem, and you also can find out reactive power, because why I am saying is reactive power is important, because this is what you are feeding from the supply, but this is same as a motor or generator, okay. And if S is the volt ampere, 3 VSS, so S cos phi is the power at the grid, S sin phi is the reactive power at the grid. So, at the grid you know V, you know I, you can find out the Vi, you can find out the P and Q in the grid. Is it okay? Now, you also know there is a induction machine work on motoring zone, work on generating zone or a braking zone. I hope you are aware of this. 3 zones in which can work or regions. And motoring, you say the speed is from 0 to 1, motoring is speed from 0 to 1 and the slip is from 1 to 0, and generating speed goes from 1 to 2, 1 to 2 is the speed and the slip is from 0 to minus 1, okay. And braking is minus 1 to 0, braking is speed is minus 1 to 0 and the slip is 2 to 1, okay. If slip more than 1, it is a braking mode. So, these 3 regions you are aware of, okay, right. I think this is the repeat of the same thing, right. And then you also know in each of the zones there is some regions which are stable which and some which are not stable, that also I hope you know. So, in the motoring you know there is a 0 to some S max is the stable zone and the other zone is unstable zone when the slip is from 1 to S max, right. In generating is when 0 to minus S max Tg, it is the stable zone. Then if the slip goes beyond S max T in the negative direction, it becomes unstable zone, okay. And in the braking there is no stable zone, whole region is unstable, right. So, you are I think you are aware of this anyway. I think you know that if you plot, so you have a curve like this is braking, motoring, generating and this is the region it will go, and this is supposed to be this is the stable zone, is not it? Stable, all other are unstable. Is not it? So, I think we need not have to spend more time, you are supposed to know this in your basic theory of induction machines. Okay. Then some of the critical performance you are interested in starting current, starting torque, maximum torque, slip at maximum torque. These are the critical parameters of the motor, right. Then you plot, you can plot current, slip, efficiency, torque, speed versus power output. This is the load characteristics, okay. You know the efficiency will go like this, sorry, then current will go like this, then similarly power factor, everything will change as the power increases from 0 to 1, okay. So, this what you call it as a load characteristics, this whole thing is in stable zone only. Power in 0 to 1 is in stable zone, it will not go to unstable zone, okay. So, these characteristics I hope you are aware of, right, how it varies. Now, the power flow you feed power through the terminals, then some power is taken out by the stator copper loss, then some power is taken out in the core loss, then you have the air gap power out of which some power is taken out in the rotor copper loss, then what you get is the developed power in the machine, then some power is taken out in as friction windage, what you have the output power, okay. So, that is how the power flows here. I think this also you are aware of, okay, it is very simple, right. Yeah, 5 minutes. Okay, phasor diagram. Okay, now you can draw the phasor diagram of motor with motoring conventions, right, that is neglect core loss etc. and low slip, okay. Then these are the right, okay. I think this will be a starting point for the next lecture. Phasor diagram as motor you have a air gap power, air gap voltage, okay. Then you have the no load current, magnetizing current, core loss current, then you have the stator current, okay. And then you have the stator resistance and leakage reactance, you have the Vs. So, Vs is the input voltage, Is is input current, and this angle is the phi s. So, this from the equivalent circuit you can draw the diagram, but you start from Vg, right, it is convenient to draw that. So, you can draw the phasor diagram as a motor, okay. And then you can if you the two things now I want you to, before we take the next lecture, important thing is we were saying motoring and generating. In motoring S1 was positive, speed was less than 1, is not it? Speed in motoring, speed was less than 1. In generating, you call it as S2, which is negative, okay, and speed will be more than 1. So, we will take up, you know how to operate at this point. This is the motoring, where slip is, this is 0 slip or a speed is 1. So, this is the speed, I call it as nu 1, slip as S1, which is positive, and torque is positive here. This is the point of interest. So, as of now you know how to find out this. All that we do is just make it negative. Supposing instead of S1 you make it S2, which is negative here, okay. When S2 becomes negative, what happens? Your torque becomes negative. So, this from this, instead of this point you are operating at this point, is it okay? Your torque becomes negative, your slip becomes negative. So, S2 dash or minus S2, I call it as S2 dash as minus S2, which is positive, okay. So, this is what we will try to take up, right, as a performance equation of generator with motoring conventions with negative slip, okay. So, this is what as a generator we will take it up in the next class. So, we will close it here now. Okay.